A classical electron is moving in a circular orbit of radius 1 angstroms with angular momentum h bar joule seconds. Calculate the field generated by the electron at a distance of 3 angstroms from the center of the orbit and along its axis. So I note that if this electron is moving in a circular orbit with constant angular momentum, this will imply that the electron is performing uniform circular motion. So if I consider the uniform circular motion of an electron with radius capital R and tangential speed v, we can see that this capital R here is 1 angstrom, 10 to minus 10 meters, and we're looking for the magnetic field at a distance 3 angstroms from the center. And I recall from the previous problem that the magnetic field at a general point P at a distance a from the center of a circular coil is given by this expression. So first I need to consider what the current the electron establishes will be. So we can note that an electron moving in a circular orbit with a period t establishes a current, the charge of the electron minus E divided by the period. The minus sign indicates the current opposite to electron motion direction. So current flow is in opposite direction to electron motion. Now we can calculate this period. The period t is basically 2 pi r, the circumference of the circle, divided by v, or we can say that v is equal to the distance it travels, 2 pi r in one period, 2 pi r over t. So with that, the period can be written as 2 pi, since so we're not using lowercase r here. This is 2 pi capital R divided by t. So capital R is 10 to minus 10 meters. So it is 2 pi 10 to minus 10 meters divided by v. This must be in meters per second. And you can see that the r hat vector or r vector is perpendicular to the tangential velocity vector here. So we have a 90 degrees in between these two. So this is my r vector, if you wish. R vector and v vector are perpendicular to each other. So the angular momentum r vector perpendicular to v vector on a circle. So if you want to write the angular momentum which is r cross product with the linear momentum, has a magnitude mv capital R here. So this r vector is capital R in r hat direction. So it's going to be equal to mvr. So, and this angular momentum is given to us as h bar, which is Planck's constant h divided by 2 pi. So we can write the tangential speed as h bar divided by m capital R, or if you calculate this, this is 6.63 10 to minus 34 joule seconds divided by mass of the electron 9.11 10 to minus 31 kilograms times the radius 10 to minus 10 meters, you will find that the tangential speed is 1.16 10 to 6 meters per second, which is much less than the speed of light. So we can conclude that this is non-relativistic electron. Okay. So for the period t, we have 2 pi 10 to minus 10 divided by v. So it's going to be equal to 2 pi 10 to minus 10 mr, mass of the electron r, divided by h bar. And this is going to be equal to h bar is h divided by 2 pi. So this will be 2 pi square, 9.11 10 to minus 31, or let's do this step by step. 2 pi squared, then we have 10 to minus 10, then we have mass of the electron 9.11 10 to minus 31, then we have r, another 10 to minus 10, and this will be divided by h, which is 6.63 10 to minus 34 joule seconds. So we can calculate the period to be 5.4 10 to minus 16 seconds. So the current, which is the charge of the electron divided by the period, will be minus 1.6 10 to minus 19 coulombs divided by 5.4 10 to minus 16 seconds. That's the period. So this gives us minus 2.96 times 10 to minus 4 amps, which is roughly 3 times 10 to minus 4 amps. So we can use the result from the previous problem to calculate the magnetic field. So the magnetic field H at a distance a is equal to 3 angstroms will be given by IR squared. So it will be minus 3 10 to minus 4 r squared 10 to minus 10 squared divided by 2 r squared 10 to minus 20 plus a squared 3 times 10 to minus 10 squared to the power 3 over 2 in z hat direction. So this will give us minus 47,434 amps per meter in z hat, minus z hat direction, or minus 596 Ørsted in minus z hat direction. So this is the SI, this is the CGS. And remember, 1 Ørsted is equal to 1000 over 4 pi amps per meter. So we can use this conversion. Okay, so this is the magnetic field. Well, this problem was given in SI, so I can say that this is the result in SI. And if you look at my setup here, so this is my z-axis. This is my x-axis, this is my y-axis. And you can see if the electron is moving in this orbit in the counterclockwise direction, like this, my right-hand rule tells me the field should be pointing up, but because it has a negative charge, the field is pointing down. So it is in minus z hat direction. So I can calculate the magnetic field at a distance 3 angstroms from the center of the circular orbit in SI units, minus 47,434 amps per meter z hat, or minus 596 Ørsted in z hat. So that's using CGS units. Okay, So this was an application of the result of the previous problem. We're considering the current created by an electron that is performing uniform circular motion with a radius 1 angstroms, and we're interested in the magnetic field 3 angstroms from the center of the orbit along its axis. And to find this, we need basically the current that is generated by this electron. And the current is the charge that flows in one period, which is minus E over T. In order to calculate the period, I used the uniform circular motion. Tangential speed is constant. It is the circumference of the circle, 2 pi r over t is v. So it is 2 pi 10 to minus 10 over v. Then I need to know what v is. The r vector, radial vector, and the position vector and velocity vector are basically perpendicular to each other on a circle. So the cross product r cross mv is equal to mvr, which is equal to h bar. It's given as h bar in the problem, which is h over 2 pi. So I can calculate v from here to be 1.16 10 to 6 meters per second, which is much less than the speed of light, which is 3 times 10 to 8 meters per second. So that is speed of light. So it is a non-relativistic electron. Now the period will be 2 pi 10 to minus 10 divided by v. So if I substitute for v 1.16 10 to 6 meters per second, I will find 5.4 10 to minus 16 seconds. Substituting that for the current minus E over T, we find minus 3 10 to minus 4 amps, or minus 0.3 milliamps. That's the current created by this electron. And the magnetic field, I can just substitute for the current minus 0.3 milliamps. It gives me the answer in minus z hat direction. So following the right hand rule, if you look at the direction of the electron motion, you curl your fingers in the direction of the electron motion. The thumb points up in plus z hat direction, but because of the negative charge, the magnetic field is in minus z hat